So now we're going to actually apply a titration of a weak acid with a strong base, NaOH. They gave us 50 milliliters of acetic acid at a concentration of 5 times 10 to the minus 3 molar, titrated via, they said via, the base NaOH with a concentration of the base 10 to the minus 2 molar. Just as a reminder, we can again do a titration curve, which is where the x is either the x-axis is either volume or the x-axis is x variable, where this variable is a progression of the titration VB at equivalence. Again, the curve doesn't really change whether you do it with VB or VB at equivalence, just the numbers in the x-axis will change, as you will see. Okay, write the titration reaction, that's part A. And part B, they asked us to calculate the pH at VB equals 0, VB 12.5, VB 25, and VB 50. Now I want to point out right away, when they say VB equals 0, when x is 0, that's initial. When you see VB equals 12.5 and you see that the x is 0.5, that means that when the x is 0.5 for a monoprotic acid, that automatically tells me that this is the half equivalence point. VB equals 25, where x equals 1, that automatically tells me when this is equal to x is 1, that means that VB is equal to V at equivalence. So automatically my volume at equivalence is 25 milli. And VB equals 50, that means, and when they say x is equal to 2, that means this is 2 times the V at equivalence. Give the equation of pH as a function of f of x, and for 2 values. Draw the shape of the titration curve. All right, so first of all, I'm going to show you a graph where my x is just simply my volume, okay? My x-axis is volume. And we already saw that such a curve looks like it has a buffer region. It has this slight increase in pH, initiation value, and then a more or less steady, hardly any change in pH in the buffer region, and then a rise, not too sharp because it's a weak acid, but there's a straight line more or less at the equivalence point, and then excess, the pH is suddenly higher. Again, notice the volume at equivalence, the pH of the equivalence point will be greater than 7 for all titration curves of a weak acid with a strong base. Half equivalence, we already know actually the V equivalence is 25 because that's when my x is equal to 1. And when my x equals 0.5, that's my V half equivalence. And at half equivalence, you should also know already the pH value, because at half equivalence, pH is going to equal to pKa. I'm going to, of course, prove that to you with the calculation in a moment. We're also going to say that at equivalence point, all of my HA initial at equivalence is going to become A minus. A minus is a simple base, and that's going to be 7 plus half pKa plus half log of A minus. And we're going to calculate the concentration of A minus after dilution, and dilution by the titration, of course. You're going to see that the pH will be 8.13. This is the shape of the curve of a weak acid titration with a strong base, acetic acid. Of course, the equation, part A, they asked for the equation. And the equation of the reaction is acetic acid with OH minus. Of course, there is an NaOH, but you just can put OH minus, is CH3COO minus. Now, if you wanted to put the Na, you would put it as CH3COO Na, and then that would be NaOH plus water. All right, so we just put down the values that were given, and I can, if I didn't notice anything about the X value or anything and whatnot like that, I can always calculate V at equivalence. Of course, you know that at equivalence point, the number of moles of acid is equal to the moles of base. So CaVA equals CB. Now, what is CaVA? Concentration of the acid times volume of the acid. Notice the volume here of the acid was given as 50 milliliters. Concentration also was given. Concentration of base was given 10 to the minus 2 molar. And I have to calculate VB at equivalence. This is the volume at equivalence. Calculate it, you get it 25, which we already knew from our X value. Okay, part B. Calculate at the pH at VB equals 0. When my volume equals to 0, what happens? What do I have? If I had no NaOH added, you all know that we have only a weak acid. And if I have only this weak acid in my solution, how do I get the pH of a weak acid? Yes, you see, if the concentration is greater than or equal to 100 Ka, here's my concentration. There, I didn't dilute, I didn't do anything to it. Is it greater than 100 Ka? My Ka was 10 to the minus 4.74, because the pKa was 4.74, times 100 is going to be 10 to the minus 2.74. Take that value, check it, or see if concentration divided by Ka is greater than 100. Indeed, it is, and therefore, what calculation? Yes, of course, great, you're so smart. pH equals half pKa minus half log C. Because you memorized this right now, right? Of course you did. Now, if you wanted also, remember this came from in the Ka, but X is negligible in the denominator, and take the log of both sides, you get this equation. But of course, all of you should just memorize this equation, make sure that there's a negative sign here. pH equals half, pKa substitute, concentration substitute, get a number. Check it out. Is this pH less than pKa minus 1? This is the second validity or a further validity to make sure. Indeed, this pH is 3.52 is less than the pKa minus 1, and therefore this is valid, and therefore the use of this equation is also valid. Again, but we didn't need that because we had seen that concentration is greater than 100 Ka. Okay. Now, at half equivalence, when the volume is 12.5, X is 0.25. Of course, you should have noticed this volume is indeed half of my 25. No calculation is required. You don't have to do a chart. You don't have to do anything. This is half of my, right in the middle of that buffer region, and the concentration of the acid will equal to the concentration of the A minus, the conjugate of the acid, pH equals pKa. Now, I will show you the calculation, but there's no need for you to do it. And let's do that right away. Let's see how we do calculations overall, not initial, not at initial concentration. Whatever the whatever volume I added. It doesn't have to be any particular volume of base. Take CaVA. That's the millimoles or moles of acid. And take the concentration of the base times the volume of the base. See what they are. Okay, so concentration times volume, again, I use the volume in mils, so this is millimoles. Concentration times the volume, I use the volumes in mils, so this is millimoles. Do the calculation. Concentration times volume, look at the numbers that you get. 0.25 for the acid, 0.125 for the OH minus. Clearly, my OH minus is my limiting reagent, surely because I did not reach equivalence point yet. But even if I don't think about that, this number tells me it's limited. So it's going to run out. It's going to become 0. So what's going to react? This is going to be 0 here. I'm going to take 0.25 minus 0.125. So I'm left over with, so I'm going to take CAVA minus CBVB. Here, CBVB is 0. And here I'm going to produce CBVB. Now, what do I have in solution? What is left in solution? Yes, I have acid and its conjugate. What is that? Yes, acid and base, common ion effect or buffer effect. When they have high concentrations like that, you get more like a buffering effect. pH comes from where? Anderson. Okay, let me change that. Okay, of course, from the Henderson, and the pH from Henderson, pH equals pKa plus log of the base divided by acid. pH equals pKa only. Why? Because the acid is equal to the base, and you're done. Now, let's say this VB was not half equivalence. It was some number below that. Well, whatever number it is, I will have a different concentration here, a different number of millimoles. You still have base divided by acid. You still have acid and base in your medium. So that's when you use the actual Henderson and you substitute the concentration of acid divided by the base. At 25, at equivalence. Of course, at equivalence, what happened? Yes, all the acid got converted to A minus. Let me just show you with this here. If I put V equals 25, VB equals 25 mils, and you multiply these numbers, of course, this number doesn't change. It's still 0.25. Here, if this was 25, this would also be, OH minus would be 0.25. So I have equal amounts of acid and the base. So both will be reacting completely to 0 and 0. And all of everything got converted to the acetate. So now I will get 0.25 moles of acetate, or CAVA, divided by, if I want concentration and I need the concentration, you have to divide it by the total volume, which is Ca plus Cb. What do you have here? Yes, it's a weak base. So to get pH of a weak base, you ask yourself, is concentration greater than 100 kb? Or assume that it is, and you use the equation pH equals 7 plus half pKa plus half log C. And don't forget, this concentration is that amount, the concentration of the A minus, with the volumes taken into account. Substitute in, and you get pH is 8.13. Okay, so check it, because I didn't really check if concentration is greater than 100 kb. I need to check this number. Is the pH greater than pKa plus 1? Remember, for bases, I say pH is greater than pKa plus 1. And notice, guys, remember when I first talked about acid-base equations, and I told you all you really need is that first chart there at the beginning? Really, look, this is, we're back to this equation. We're back to checking if pH is greater than pKa plus 1, if it's valid. Check if it's valid. Indeed, this pH is greater than pKa plus 1, and therefore use of this equation is okay. Now, at 50 milliliters of added OH, notice I didn't change my equation. My equation stays the same. Guess what? I also don't change. This is still CAVA, and this is still CBVB. The CAVA doesn't change. It's always the same, but the CBVB changes, because the milliliters that I have added now is greater. Again, we start from scratch, as if I didn't add anything before. Now, look at this. I have OH minus is in excess. Why? Of course it's in excess, because I'm after the equivalence. So what do you do now? Yes, you take we're going to have excess OH, so CBVB minus CAVA, where CAVA will tend to 0. So that will be 0.25 minus 0.5 minus 0.25 is indeed 0.2. What's this concentration? Yes, now this here, the A minus is CAVA, the limiting reactant amount. Mixture of weak acid, weak base, and a strong base. That's what we end up getting is a mixture, OH minus and acetate and the acetate. So that's 2 bases, strong base with a weak base. So what's the pH? Of course, you choose the pH from the stronger base. So this is a mixture of 2 bases. We choose only the stronger base. Hopefully, we're in a region where only the stronger base takes place. You do need the concentration. You have to get the new concentration, which has been diluted. We got the number of millimoles, that's 0.25 millimoles. You have to divide that by the total volume, which is 50 mils of the acid plus the 50 mils of the base added. And that gives you this concentration of excess OH minus in my solution, which will determine the pH. Get the pOH, which is minus log of the OH, and then get the pH, which is 14 minus the pOH is 11.4. And indeed, that's very logical to be in such high pH because I'm at the end of my titration curve. Great. Now, what did they ask for part C? They asked for a derivation for part C, and they asked to derive a general pH equation, but in terms of X, okay? Where X is between 0 and 1. When we say X is between 0 and 1, what do we mean? Well, remember, what is X? X is VB divided by VB at equivalence. Okay? If it's between 0 and 1, that means I have not reached equivalence point yet. So I'm in the buffer region, okay? If I'm in the buffer region, of course, the first buffer region. Well, I'm just gonna do a derivation here. If I multiply top and bottom by CB, top and bottom, that's the same thing. And remember, CB, VB at equivalence is simply also equal to CA-VA because that's the idea of equivalence point. The CB-VB at equivalence is also equal to CA-VA. Now, why did I do that? You will see in a moment in time. Okay. Overall, remember, I have the same equation, CA-VA for the acid, CB-VB for the base. What region am I in? Before equivalence. So my base is going to run out. So that's going to be 0. This is going to be CAVA minus CBVB. And the concentration of A minus is CBVB. What do you have? Yes, you have a mixture of acid and its conjugate base. And so we use Henderson. Remember, buffer region. Substitute the concentration of base. Of course, you don't really need to do concentration. You could just simply use millimoles because that's divided by total volume on the numerator and total volume on the acid side denominator. So the total volume actually cancels. So what do I have here? CBVB divided by CAVA minus CBVB. I personally like to use this equation to do the calculation all the time for anything in the buffer region. Okay? So you do that, make sure you put that. That's always a nice way. I also really love the chart. It's easy to write down. It doesn't really waste your time. Some people think that it wastes time. I don't. That's why they want you to have this type of equation. So you memorize it and you substitute right away. I'll tell you that I don't like it, but if you guys want, go ahead. You can use it. Okay. Clear? Again, like I said, I like the chart. But if you just like to memorize, feel free to do that. Always the concentration of the A minus is simply coming from the base because that's my limiting. The leftover acid is CAVA minus CB. Okay, now I'm doing a derivation, right? So let's say, let's divide the top and the bottom by CAVA. Now the question is, why am I doing that? You're going to see. What is CBVB divided by CAVA? We just derived that right on top. That's just, okay? And the denominator here, if you divide by CAVA, here, that's just 1 minus x. And thus, at any value, if I give you 3 or 4 values for volumes, you know, if you're going to sit there and write the chart, yeah, that'll take a lot of time. But if you simply use this equation, pH equals pKa plus log of x divided by 1 minus x, all you have to do is take the volume that they asked you for divided by VB at equivalence, you get the x value, and you substitute into this equation. So yeah, it's kind of an easy way out from doing all the other calculations. Now, however, this is always before equivalence, okay, and in the buffer region. If I'm talking after equivalence, okay, after equivalence, where after, not at equivalence. At equivalence, you don't have an equation, you simply have the A minus in solution. After equivalence, let's look at what we have. Again, we have then the same equation, CAVA for the acid, CBVB for the base. But now, if I'm after equivalence, that means my base is in excess. My acid is limiting. Okay, so if my acid is limiting, that means it's going to tend to 0. The leftover base will be CBVB minus CAVA. The produced acetate will be the limiting reagent, which is CAVA. What do you have here? Yes, you have a mixture of acid, strong acid, and a weak, strong base and a weak base, as we said before. The pH is only going to be determined by the base. OH minus is going to be CBVB minus CAVA, which is that moles, divided by total volume, which is CA plus, VA plus VB. And this is always the case, and yes, you may use that. And the pH, of course, is, well, you can get POH, which is minus log of this concentration of OH, and then get the pH. Okay. So pH is plus log the concentration of the OH minus, so I just substituted. If I divide the bottom of this equation and this equation by CAVA, why am I doing that again? Again, I want something in terms of x. Here we're just complicating it more than it has to be. And again, this is just an equation in terms of x. I recommend that you never use this. There's no need. It's more complicated than just do the chart. Okay, so this will be 14 plus log of CAVA divided by total volume plus log of the x, because if you do that, that would be x minus 1, right? Okay. Well, that's just the, you know, the question was asking for some derivation of pH in terms of that x value where we don't have, I guess, volumes or something. Clear, there's never a need for use of this equation. It's more complicated than the use of the other equation. This is a graph in terms of x on the denominator. This is 0.1, 0.2, 0.5. We said is, looks like it should be point. And here's my buffer region. Again, nothing changes whether I have my x value here as x, my x, or as volume. That you still have the same shape of curve as if you had volume with the same pH here, doesn't change. Number 49. We're going to titrate now a 10 milliliters ammonia, a base, with HCl, hydrochloric acid. They gave us the concentration of the hydrochloric acid, which is 10 to the minus 2 molar. And they told me that the equivalence is obtained when we added 10 milliliters of the acid. So look at what they gave you here. They told you what the equivalence point is. And so this is actually the truth of titration, is where I do not have the concentration of my unknown species or analyte in my beaker or in my volumetric flask. And once after I reached 10 milliliters of the added acid, whoop, I saw a color change maybe in my indicator, and that helped me to know that I have reached my equivalence. Okay, so some of the questions that was asked: what is the titration? And calculate the unknown concentration of the ammonia. And then after different volumes of added acid, what would the pH value be? Give the equation again for pH as a function of X for just the buffer region, and draw the shape of the titration curve. Okay. Well, I'm going to draw the titration curve first, just as an example. Remember, if I have a weak base and it's going to be titrated with a strong acid, this is what it looks like. I'm high pH. I have, a little bit of a kink here, initiation value. Then I have a buffer region, usually a little bit longer. And then I have at V equivalence, more or less of a straight line sloping down with a sharper increase in pH. And then I have excess HCl. So if I start off with NH3 as my initial point, and my buffer region at half equivalence, I will have the equal amount of ammonia and ammonium, which is going to be produced. At equivalence, all of the ammonia would be converted to the NH4+, and after equivalence, I have both, of course, the NH4+ and the HCl, but the HCl is in excess. Okay. Okay, so first of all, our equation is the base ammonia reacting with acid HCl, or simply H3O+, to give you, and the ammonia will pick up the proton from the acid, and it will become ammonium and H4+ and water. So we have, of course, given we have concentration, milliliters of the ammonia. We don't have its concentration. We have the concentration of the acid and the volume at equivalence. Okay? So here we have CAVA equals CBVB, where here the acid is my titrant, and so this is VA at equivalence, and thus I can calculate the concentration of base. Now, you could only do this at equivalence point, guys. You cannot calculate the concentration of the base unless we have the equivalence. So this is the concentration times the 10 milliliters, which is my equivalence, CB times the 10 milliliters, which is my starting volume of my base. And we get that the concentration of the base was 10 to the minus 2 mole. Now they want us to calculate number of pH values at different volumes. Okay, so we're going to do that. When the volume of the acid added is 0, or X is also 0. Of course, if I haven't added anything, I only have what's in my beaker, and that's simply ammonia, which is what? A weak base. How do you get a pH of a weak base? Come on. Yes, of course. You say it's going to be 7 plus half pH if and only if, after I do this equation and I put the concentration, put the pKa value, since they gave me pKa values, if the pH of the result is greater than pKa plus 1, then this equation is valid. Now with titrations, yes, I would recommend to do this because, going through the quadratic is a little bit more complicated. But I will tell you, it doesn't always work, okay? So anywho, this is valid, so you're okay with using that equation of a weak base when the condition of the concentration is greater than 100 kb, right? Okay, so what if the volume now is 5 milli? Okay, if I added some acid, okay, 5 milliliters, you should recognize that that's half of my V at equivalence because V at equivalence was 10. So that means that's when the concentration of ammonia equals the ammonium, and that means that the pH equals pKa. And you don't really need to do a calculation other than that. At equivalence point, what happens at equivalence? Yes, everything got converted to the ammonia. Again, guys, what you can do is, yes, you should be able to put a chart. This is CAVA equals CBVB equals CAVA. Get the moles chart and see what you have. Everything got converted at equivalence to the ammonium, sorry. What's everything? Yes, all the base got converted. So the base, CBVB, which is 10 to the minus 1 times 10 milliliters, because we use that amount, divided by total volume, that's the new concentration of ammonium in my solution. What is ammonium in the solution? Yes, it's simply a weak acid. So is the concentration greater than 100 Ka? If it is, the pH is going to be half pKa minus half log C. Indeed, we check it. Substitute the concentration that you just calculated, substitute the pKa, that's 5.25. Indeed, you get pH is less than pKa minus 1. And that is valid, and therefore the use of this equation is also valid. And you could also check it from the Ka and the concentration. Very simple. Again, if you still don't get it, write the chart in detail. CAVA, CBVB, and see what is left over after each time. At some point, you do have to get faster. Okay, so here is, at V volume equal 20 mils. Okay, so it's a little bit, let's see. Now, as an example, CAVA, this is the concentration, sorry, CBVB. That's the base times its volume, again in milliliters. So this is millimole chart, CAVA. 10 to the minus 2 was my concentration of HCl times the volume, which I added, which is 20 mils. So who's in excess? Well, let's multiply it. Yes, you can see that already the acid is in excess. This is simply going to be 1. This is going to be 2. So that's going to tend to 0. That's going to be 2 minus 1, which is 1, and the concentration of ammonium is 1. What do you have? You have mixtures of two acids. I have a strong acid left in solution, excess amount, and I have a weaker acid, ammonium, produced in my solution. Of course, the pH is going to be determined from the strong acid, but I need its concentration. I have its millimoles. Do not forget to divide by the total volume. You have to here divide by the total volume, which is 10 for the ammonia plus the amount added for the acid, which is 20 mils. You get a new concentration of H3O plus. pH is simply log of the H3O plus in solution, and you get the pH. Of course, the pH has to be quite acidic at the end of the titration curve of a weak acid with a weak base, with a strong acid. Now, again, the derivation in the buffer region in terms of X. So again, what is my X value in this case? Now it's the volume of the acid divided by the volume of the acid at equivalence. I'm going to multiply by CAVA top and bottom. And why do I do that? Again, in order to get this type of ratio, CAVA divided by CBVB, because CAVA is CBVB. Likely you will never be asked to do the derivation on an exam. Again, this is MCQ, but we're doing this to give you an equation which you can use if you like in any buffer region. Ammonia, again, this is my equation, plus H3O plus CBVB CAVA. And again, this is also done so you can see the calculations easily. If I'm in the buffer region, that means I haven't reached equivalence. That means my acid is my limiting reagent, so it's going to tend to 0. I'm going to have some leftover ammonia. The leftover will be the initial moles, CBVB, minus the moles of the acid, CAVA. The amount produced of the ammonium will be the limiting, which is the CAVA. What do you have? Of course, you have an acid and a base mixture, so you have Henderson. PaKa plus log of the base divided by acid. So I simply did the moles. Again, we didn't do the total volume. There's no need here. You should just use the millimoles. Know that by now. Now we're doing a derivation. So we're going to divide by CBVB, divide by CBVB. Why do I do that? I do that because CBVB is divide by each other is 1, and CAVA divide by CBVB is the X value. And thus, look at this. This is a nice equation. If you have any volume within the buffer region, okay, and you know the X, that take that volume of the acid divided by the volume at equivalence, you get the X value. At any volumes, you can simply substitute into this equation. And yes, I mean, you can use this. You have to memorize it. You don't have to derive it at any time. I simply also still like this equation. I like the chart, like I said, CAVA. This is very simple to do when you do it, but it's up to you. Okay, so here's a titration curve. They asked us to draw it. I have to put the initial pH of the ammonia, go down and do a concavity, cave up to the half equivalence at 5 mils. Always put a value for the half equivalence because that's simply equal to the pKa, that's a pH. Put another value for at the equivalence point, which you should have gotten the pH for it because it really is necessary to draw a curve. And one value after equivalence is more than enough. You don't need too many values. Again, notice I only need the half equivalence, but I can't put another number, to get the nicer curve, to know how this really curves, but you don't have to. You can just have half equivalence, at equivalence, and kind of add the points to draw the curve. Okay,